So I want to talk today about, first of all, the idea of a universal mapping property. Universal mapping property is a way of using the language of category theory to give a characterization or definition or specification of a structure or structured object in a way that's unique up to isomorphism. It picks out a certain kind of structure in terms of its mappings to other objects in a category. So the simplest example, or well, maybe the first example historically of such a thing, is the definition of a product of two objects in a category that was given by MacLean in 1949 or something like that. So we'll start with that. Well defined. So in any category, a product of objects A and B consists of the following. Well, an object, which I'll for the moment write P, equipped with arrows to A and to B, with the following universal mapping property. Given any object X and any arrows into A and to B, there exists a unique map U from X into P, making the two triangles commute. So let's, in order to write that down, let's give these things some names. So I'll call this one P1 and this one P2. And now the idea is that this structure here is a product, just in case, given any X and F1 and F2 as indicated, there exists a unique map U, that's this one, such that P1 after U is F1 and P2 after U is F2. So, and now just a little bit of notation. When we have a product like that, we usually write P with the usual Cartesian product notation, and we call these things the projections. P1, P2 are called projections. And then we write the unique map U, determined by F1 and F2, in the form F1, F2, using the pairing notation. And then the equations become P1 of F1, F2 is F1, so that's the familiar projection equations. F2 is F2. Okay, so that's the idea of defining a product in terms of mappings to, and in this case from, other objects in the category. Let's look at some examples. Well, first of all, let's have a basic result about products. I said that these universal mapping properties determine things uniquely up to isomorphism, so let's just check. Fact, products are unique up to isomorphism. Products are unique up to iso. So what does that mean? Well, let's suppose I have here A and B, and I have two products. So what I want to say is, if I have two different products, like this one and this other one here, well, then they must be isomorphic. So that's my claim. Okay? Any two products are isomorphic. So let's see how to prove that. We'll take one here, say A cross B, with its two projections, P1 and P2. And let's take another one here, A cross B, with its two projections, we'll call them Q1 and Q2. And now, if this one is a product, then this is some object with a pair of arrows, then there must be a unique arrow here, namely P1, P2. And if this one is a product, let's rewrite it down here. Nope, P1, P2. If this one is a product, then because this has a pair of arrows, there must be a unique map here, Q1, Q2, making these two triangles commute. And now let's see what happens if we compose these two arrows with each other, okay? So if I compose these two arrows like this, and then I take follow that with the projection by P1, well then because this triangle commutes, that's the same as just going across here. Yeah? So going down and across here is the same as going like that. But now this triangle commutes, and so that's the same as this. Right? So the whole thing composed with P1 is P1. And similarly over on this side, the whole thing composed with P2 is just P2. Yeah? And so the whole map coming all the way down here is just the pair P1, P2 on A cross B. Yeah? However, the identity map from A cross B to itself also has that property. Right? And so it follows that this must be the same as the identity on A cross B. Because if I put the identity map in here and compose it with P1, I'll get P1. If I put the identity map here and compose it with P2, I'll get P2. And by the uniqueness clause, which is right here, right, this uniqueness part, this vertical composite must be the identity. And so I've shown that the composite of these two maps is the identity on A cross B. But of course, the whole argument is symmetric. So if I do it the other way around, I get the identity on A cross prime B prime. And so I have an isomorphism between the two. Yeah. I have maps going back and forth, the composites of which in each case are the identity maps. So that, yep?
Is the uniqueness of that definition, or is that derived?
That's the definition of a product.
Okay, thanks.
In that sense, the universal mapping property characterizes this structure uniquely up to isomorphism. Right? Any other structure with that same property will be isomorphic to this one. So let's look at some examples of products. So for example, well, of course, in the category, so not every category has products, right? And some categories might have products for some objects, but not for others. But lots of familiar categories always have products for any two objects. So in sets, the product of two sets is just the Cartesian product. That is, the set of all ordered pairs, and let me write curly parens here to distinguish between these things and my pairing operation there, with A an element of A and B an element of B. So in the usual set theoretic construction of Cartesian products out of ordered pairs, this set of all ordered pairs, together with the usual projections pi 1 and pi 2, is a product in this sense. So it's uniquely determined up to isomorphism by that property. And it doesn't really matter how you define this pairing. There are lots of different ways of defining pairing in set theory, and any one that you choose will give a product, categorical product in this sense. Similarly, in topological spaces, in posets, you have the usual products of structures. So let's look at posets, for example. If I have two posets, P and Q, I take the product poset. That's going to be, well, the underlying set will just be pairs like this, and then I'll order those pairs by saying PQ is less than or equal to P prime, Q prime, just in case. And then I put the product ordering on there. So I say P is less than or equal to P prime in P, and Q is less than or equal to Q prime in Q. And then what I have to check is, yep?
Also do an OR?
No.
Okay. Well, like lexicographic ordering.
You could order this in lots of different ways, but I claim it won't give you a product in the category. And that's the interesting thing here is we have this definition that tells us what a product has got to be, right? And so that serves as a guide for how to order these things. There are lots of different ways of putting an ordering on this set, right? And they will give you different orders, different posets. But in order to actually make it be a product in the category, there's only one way, up to isomorphism of posets. And so what we have to do is we have to check that this particular specification is the one we want, and that means checking that it has this universal mapping property in the category of posets, which I'm going to do right now after I answer this question.
I'm confused about P1 and P2. They look like arrows, but are they, is that part of the existential thing, that there exists a U and a P1 and a P2, or where are they?
So a product of objects A and B consists of a triple, P, P1, and P2, such that for all. One way of thinking of it is, it's a universal gadget of this form. Okay? So give it a map, an object equipped with two maps, one into A and one into B. So it's one of these, and every other one maps into it. It's a universal such gadget. That's the structure is the whole thing.
That's a related question about just the diagram notation.
Yeah.
So how much, so the diagram is a kind of slightly informal picture of the more exact thing on the right.
Yeah.
Which parts of the stuff on the right are missing from the diagram?
You mean in terms of
So how much of
rendering or something like that?
How much of the stuff on the right could we uniquely read off if we weren't given it, as we were just given the diagram?
I don't think you can't recover the whole thing, because you need the order in which these arrows are drawn.
Exactly, and also the bang is missing.
The uniqueness, yeah. I mean, the custom is this dotted arrow means there exists a unique thing, given the rest of the problem. So, I mean, I guess you could say, here, the product of these objects is this part, so that's kind of given first. And then you'd have to say, somehow, for all things like this, there exists a unique one.
So once you drew the PP1 and 2, the rest pretty much falls.
Okay. I mean, in general, the universal mapping property is going to be something of the form, it's a gadget of this structure, which is universal, in the sense that given any other gadget of that structure, and now you have to know to map into it or map out of it. There are left and right variants. Okay, so let's just see that this is really a product. Category post sets, just to kind of see what's going on here. Here's P1 and here's P2. Well, first of all, we have to check that these projections are monotone to make sure that this really is an object in the category of post sets. But that's, by the way I've defined this, they're obviously monotone, right? Because if this is less than this, then each of the projections is also going to stand in the relation. So that's a good diagram in the category of post sets. And now I say, give me some other post set and a pair of monotone maps, F and G. How am I going to find this thing? Well, what I'll do is I'll just take the set theoretic pairing, the pairing function, F and G, right, which I know exists because of this case, because I have products. And the underlying set here is just the product in the category of sets. And then I just have to check that this thing is monotone when I define it in that way. So I need to check that the map FG is monotone. So for example, if I have x less than or equal to y, I need to check that this is less than or equal to f g y for x less than or equal to y in the post set x. But what is this? That's just the pair fx gx, and this is the pair fy gy. And now when is this thing less than or equal to that? Well, just in case f of x is less than or equal to f of y, and g of x is less than or equal to g of y, but that follows from the fact that f is monotone and the fact that g is monotone. So the diagram I started with was in post sets, and so f and g are monotone, and therefore this map is monotone. So that thing gives me, and now I've checked that it has the universal mapping property, so I know this is the right way to order the post set. Thanks for that question. That really came in handy. All right, so that's an example. And there are lots of other examples. I won't go through them, but I'll just mention some. For example, in cat, we could wonder, does cat have products? Well, I would have to find for a category C and a category D a way of making a new category, a product category, with a couple of projections down to the individual categories. Anybody have any ideas? This was an example, the first example that I gave last time of a construction of new categories out of old. So last time I showed you how to make a product category. Nobody complained and said, why is that the product? It just looks kind of product-y, right? But now we know that it was right. At least once we check that it has this universal mapping property, Remember this category I defined the objects were pairs, C, D, and the arrows were pairs of arrows. That category has this universal mapping property, and that tells us we defined it in the right way. Right? It's a way of checking that you're doing things right, so to speak. So that was an example. Another example is, well, actually this one restricts down to this one, right? Remember we had these two aspects, or two dimensions of the notion of a category, the poset dimension and the monoid or group type dimension. We have lots of arrows and few objects, lots of objects and few arrows. So this is just a specialization of that to the posets. And of course there's another specialization to monoids or groups. So in monoids or groups, you get the usual notion of a product monoid or product group, just like in your algebra course. If you had an algebra course and you defined a product of two groups, that will give you exactly this, this notion. You'll find that you check the universal mapping property, and it's a product in the category of monoids or in the category of groups. Let's try an example of a different kind. Let's take P, a specific poset. So we're not looking at a product in the category of posets, but we're looking at a product in a poset. Okay? So I want to say, let's have some, the elements of the poset, I'll write them like this, say X, Y, Z. These are all elements of the poset P, and the poset has an ordering relation, X less than or equal to Y, etc. Right? And now, what would it mean to have a product in the poset? Well, sometimes it's good to think of a poset like this as a big egg, right? And the ordering goes up. And if there is a least element, it's down here, and if there's a greatest one, it's up here, but there doesn't have to be. But in any case, the ordering is going like this. So here's X and Y, for example, and now I want to know what would it mean to have a product of X and Y. So it would have to be something here, X cross Y, and it would have to have maps into X and into Y. So in this case, that's the ordering, so it means less than or equal to here, less than or equal to here. There. So X cross Y is less than or equal to X, and X cross Y is less than or equal to Y. And moreover, it has the property that if anything Z, let me just write lines here, is less than or equal to X and less than or equal to Y, then it's less than or equal to X cross Y, where the uniqueness is automatic now because we're in a poset. So that means, so here, let's just rewrite it here. If Z is less than or equal to X and Z is less than or equal to Y, then Z is less than or equal to X cross Y. Well, of course, if Z is less than or equal to X cross Y, and X cross Y is less than or equal to X, then Z is also less than or equal to X by transitivity. Yeah? And similarly over here for Y. So this rule, using that fact, this rule goes both ways. This is an if and only if. It says that for any Z, Z is less than or equal to this thing, just in case it's less than or equal to both of them. Anybody recognize what that's saying? X cross Y, I should have used A and B or something. The cross there is interfering. X cross Y is what? Greatest lower bound? Greatest lower bound. Greatest lower bound of X and Y. Usually written like that with a meet sign. Meet. Or conjunction. Yeah? So the conjunction of two formulas, or the meet of two elements in a poset, like in a meet semilattice, is exactly the product in this setting of posets. Okay? It gives us, we take this definition, we specialize it to a category that happens to be a poset, and we recover the usual definition of a meet in a poset. Good? So we have a kind of unifying thing going on here, right? There was something else I wanted to say before we go on.
So what was the categorical generalization of these upper boundaries?
That was the next thing I was going to say. Thanks. So let's do this. Let's say, here's an example of duality. Is that the next thing I want to do? Sure, I could do that next. It fits. What is duality? Sorry, what?
The product is only defined if meats actually exist.
Well, that's always the case. In any category, the product is a specification or definition, but it doesn't have to exist.
Okay, so this construction does not work for each POSET.
In general, the definition of a product does not work for each category.
And I guess what we're saying is it doesn't even work for each POSET category.
It's not a construction, it's a specification.
It's a specification, it's a definition of what it means to be a product. Or here it's a definition of what it means to be a meat in a POSET. This is the definition of what it means to be a meat. A POSET in which any two elements has a meat, in this sense, is a meat cellulose.
Yes.
Okay? So it's not a construction of the meat, it's a definition of what it means to be a meat.
Okay, but in the case of the sets, it pretty much looks like a specification.
What?
In the case of the sets there above, pretty much...
So this is a proof that sets has products.
Okay.
Okay?
And you prove that by giving a construction.
Yes, well, there I've shown that sets has products. And similarly, the category of POSETs has products by constructing such a thing. It satisfies the universal mapping property. So in a POSET, a meat product is a meat, and then we can define a POSET is a meat semilattice. I haven't proven that the laws for meat semilattices hold just from the existence of product, but it's true. If and only if the meat semilattice, if and only if POSET P is a meat semilattice, if and only if P has a product, A, B, or all A, B, does it make sense now?
Yes.
Okay. And now you can check
That if you have a product for any two elements, that the product necessarily satisfies all the laws for a meat semilattice. It's associative, it's commutative, and so on. Okay, I think that's it, actually. It's associative and commutative. Good. So here, duality. What is a coproduct? Well, so that's kind of a cheating, isn't it? I already told you coproduct. Coproduct means, well, just by general rules of concept formation in category theory, you add the prefix co to mean it's a product in the opposite category. So let's do it like this. So we take a category C and we say the coproduct in C, that equals in C op a product. So let's do it like this. We have an object, which I might just as well start writing as a coproduct like this. And now it's equipped with a pair of maps into it rather than out of it because we're working in the opposite category. And it's the universal such thing. So that means given any other object and a pair of maps into it from these guys, there's a universal thing here, making these guys commute. So that's exactly the definition that I just gave you for a product, except I've reversed all the arrows. Yep?
Is there a terminology for the two arrows?
So just like here, there are some conventions. We write this plus sign for coproduct. We write this thing sometimes as the maybe with a square bracket or something. That's one customary way of writing that thing. And we call these things I1 and I2 the injections rather than projections. Okay, so that's the customary jargon. Okay.
Have universal property? Yes. Some sort of a general name for just three objects and arrows going from the outside to the inside.
Co-span.
Co-span. Okay.
So we know
By duality that, so we know that when they exist, coproducts are unique up to isomorphism. I don't have to repeat that argument, right? I could take that, if I wanted to, I could take that argument, turn all the arrows around, and I would get another argument that proves that coproducts are unique up to isomorphism. That's the idea of duality. I only have to do the proof once, yeah? And then I know the same thing holds for the dual case. So here's another thing. For example, let's show whenever I have a product of two objects in a category, there's a canonical isomorphism between these objects like that. So products are commutative up to isomorphism. What's the canonical map going from here to here? Well, it's the pair, so any map into here is going to be written as a pair. It's the pair P2, P1. It's a kind of a twist there, right? Just twist the order, and that gives me a map here. And going back here, you can do the same thing. Yep. So you can check that that's an isomorphism. It's a simple diagram chase like that. It shows that this thing is an isomorphism. And then it follows by duality. The coproducts are also commutative up to isomorphism. Similarly, products are associative up to isomorphism. This, I think, is a homework exercise. A cross B. And so again, by duality, the same thing is true for coproducts. They're unique up to isomorphism. What are some examples of coproducts? So coproducts. What about in sets, a coproduct of two sets? That's the disjoint union. Disjoint union. How do you build the disjoint union of two sets? It doesn't matter as long as it's disjoint. It'll have the universal mapping property, right? There are lots of different specifications. You could say, well, just take A union B if it happens that they don't have any intersection. That would be a disjoint union. But what if they do have an intersection? Well, then move one out of the way by taking a copy of it, or put in some tags. Tag this one with everything in here with a 0 and everything in here with a 1, right? So that's a kind of usual way you could say it's a bunch of pairs of the form x, comma delta, where x is in like that is in A if delta equals 0, and x is in B if delta equals 1. You know what I mean by that, right? So that was another way of making a disjoint union. There are lots of other ways. It doesn't matter as long as you get the union to be disjoint. In posets, in topological spaces, the coproducts exist and they're built in a similar way in CAT. However, in groups and monoids, they're more complicated. Groups, more complicated. Sometimes you see these things written in the form of a tensor product because you have to kind of take the operations into account and do some extra stuff. Okay, what about in a poset P? What do you suppose the coproduct is in a poset P? Here's our picture again. So here was x, and here was y, and now it's going to be something up here, x something y plus y. It's going to go like that, and then for any z up here, right, there's going to be something like that. And then we'll have, just by duality, we'll have exactly this same rule. It'll satisfy the property that if x is less than or equal to z and y is less than or equal to z, then this new thing, x plus y, will be less than or equal to z, and conversely. Okay, so that's a least upper bound, and it's usually written as a join. That's what you expect, I suppose. Right? So all of the things follow from basically one and the same universal mapping property, just putting it into different settings. Okay, so that's that. Now here's a more interesting or different kind of universal mapping property. Maybe I need a new board for this. Well, I'll do it right here. Oh, here, let's put a fact here. So I already said over here, the joins, if they exist, the products, if they exist, are meets in the sense of a meet semilattice, and the coproducts, if they exist, are joins in the sense of a join semilattice. That means they're associative and commutative. But I guess we already showed that, right, up here. So that's the exercise that I gave you before to check that those things hold. We just checked it right there. Okay, so here's another kind of universal mapping property. This is the notion of an exponential. And it's a kind of compound thing because it's defined in terms of something else that's already been defined, namely it's defined in terms of a product. Okay? So let's suppose we have, suppose the category C has all products. That means for any two objects, I can find a product diagram. Okay? Then I'll define the exponential like this. So for A and B, an exponential is a structure of the following shape. First of all, it's an object, which I'll write like that, B to the A, together with a map across A. That's where I use the product. A map down to B, which I'll call epsilon. And now it has the following universal mapping property. If you give me anything of that same shape, some F here, mapping into B from a product with A, then there's a unique F bar such that when I put that into this diagram right here, the triangle commutes. And how do I put that into the diagram? Well, I take F bar and I cross it with the identity on A. I haven't shown you how to make a product of maps. I've only shown you how to make a product of objects. So let me do that quickly. And then that will complete the definition of this universal mapping property. So just to write it down here, it says, I have a structure of this form. And then it says for all x and for all f, there's a unique f bar of that shape such that epsilon of f bar crossed with 1a equals the f that I started with. So how do I make a product? Really, let's observe that product is a functor. So in this circumstance, right? So let's say if C is a category with products, if C has products, binary products, by which I mean any two objects have a binary product, then there's a functor product functor going from C across C into C, and it works like this. It takes a pair of objects here, A and B, that's an object in this category, to their product, and then it takes an arrow, so let's do it like this. So what's an arrow there? Well, it's a pair F, G, like that. It's got to go to A cross B. And now I have to have an arrow right here, right? And that's the arrow that I'll write, F cross G. And how does it work? Well, I put in the projections here. I'll just do one side and you'll get the idea how to do the other side. And then here I put in G, right? I do the same thing over here for F. And now I compose through, and that gives me a map from here down to B, B prime, and similarly there's a map down here over to A prime, and so I pair them up. So this is the pair of F after P1, G after P2. This is P1 and that's P2. So the left-hand side there is implicit, P2. Make sense? No, it doesn't make sense. Okay, I'll fill in the rest of the diagram then. Here's F. Here's A prime. These are the Q's, Q1, Q2. I'm not even using those. Okay? So this is the value of this functor on the pair F and G. It goes to this map. The product functor applied to Fg is this map F cross G, which I just defined here to be the pair Fp1 Gp2. Is that better? Okay. Now, you still have to check that it's functorial, right? I've given you the assignment on objects, and I've given you the assignment on arrows. But now you have to use the universal mapping property for products to see that if you compose things here, right, that this assignment will be functorial. That is, the composite of these two things that you determine will actually be the thing that's determined by the respective composites, and so on for the identity arrows. Everybody good? If you're, it's very quiet now. Okay, yeah?
I understand this correctly. Yeah. The idea is that F cross G maps products to products, given that F and G individually map elements in the product of...
No, there are no elements here. There are no... Right. So this is just a map in the category, right? It's just a map. F goes from A to A prime. G goes from B to B prime. And this is a product in the category, and this is a product in the category. So I use the universal property to determine a map going from here to here. Okay? And the universal property of this thing says, this one here says, given any object and any maps into A prime and B prime, so what are my maps? Well, they're these composites. Take those two composites. That gives me maps like that. Then there exists a map right here making the two triangles commute. Well, that map that exists by the fact that this is a product, I name F cross G. So that's the specification, just in terms of the product structure. So if I know that the category has products, then I know that that product operation can be extended to a function. It can be defined for arrows as well as for objects. And that gives me that operation that I use it.
So I think you just said, but I missed a transition from the exponential discussion to the word on the right. And so the word on the right is explaining the notation F cross.
Yeah. So in order to define the exponential, I need to assume that I have products. And then I say the exponential has this universal mapping property. And this universal mapping property involved right there, product of two arrows, rather than one. So I have to define what does it mean to take a product of two arrows. And that's what I'm describing here. Saying whenever you have products in a category, you can extend that product operation to act not only on the objects, but also act on the arrows. Take a product of two arrows. So if you have, like in this case, we have A going to A prime, I'm just repeating what I said, but maybe it's a little more clear if I do that. B going to B prime, out to G.
I can get A cross B, A prime cross B prime, and I can get a map here that's F cross G. So that's my product operation between on the arrows. And that's, in fact, a functor. So to say that it's a functor means if I go like this, I continue, right, B double prime, G prime. If I continue like that, then I can make, again, F prime here. And then the composite of these two things will be the same as taking the individual composites and making the product of them. That's the functoriality condition, that it preserves composition. Okay? All right, good. Let's go back to the definition of the exponential now, because that's what we're really interested in. It uses this producting up operation. The exponential, this is a really, I think, important and remarkable fact that you can characterize this notion of an exponential just purely in terms of a universal mapping property and the relations to other objects in the category. It gives a universal or categorical or structural characterization of a construction that in many cases is very important and sometimes complicated. So let's look at some examples. So first of all, what about in the category of sets? Well, maybe you won't be surprised that in the category of sets there actually are exponentials, and they're exactly the function sets. The set of all functions from A to B together with the evaluation function. What does the evaluation function do? Well, it takes a function f and an argument a, and it returns f of a. This structure really has that universal mapping property, and it's uniquely characterized up to isomorphism by that universal mapping property. So if you like, you can take this as a definition of the set of all functions from A to B. In posets, too,
explain how the diagram applies to sets.
Sure. Let's do that. That's a good idea. Okay, so here's the
structure that I'm proposing to be the exponential. Yeah? And let's check that this really has that universal mapping property. So we'll check. So I'm claiming, my claim is that this is an exponential. My claim is this set together with this function is an exponential. Exponential in sets. So I have to check the universal mapping property. So we'll just write it out in the exactly the same way that I wrote it over there. I put the evaluation function right here. And now let's suppose, so here's b to the a. And now let's suppose I have some function here, f, on the product of these two sets into b. So this is a function in two arguments, right? It's got an argument from x and an argument from a. So now what I need to do is I need to get f bar over here. So what should it be? Well, f bar I'll define to be, well, it takes an argument from x, and it's supposed to return now a function from a to b. Well, what should I take? Of course, I'll take the function from B to the A. Of course, I'll take the function f bar x, which at an argument A gives me f of xa. It's the lambda transpose, the currying of this function in two arguments gives me here this function in one argument, taking values in functions. Yep?
So over here when you define exponential, kind of like before when we were talking about like a product is actually a triple. So here an exponential would be like a pair of these.
It's a pair of things. It's
an
a
epsilon?
yeah.
Okay.
It's object equipped with a map of this shape,
Okay.
and it's the universal such a one.
It would be great if you could include those when you define things. Just
I
like-
did. Where is it? Right here, exponential. An exponential is this thing and that is this.
Right.
I don't get what's funny.
Just it would be easier to say to read if it also said an exponential is the pair of either the a and epsilon such that, and then the rest of the picture.
Okay.
You can read it that way, or
That's what I said. What?
Actually, it's a problem that several people have had 2 times already before. So maybe it could be a bit more explicit about what you think for a word.
Good. So the precise definitions are in the notes, folks. Okay. I'm not going to dot all the I's and cross all the T's here. I'm explaining how the machine works. If I do that, we won't get anywhere. But yes, so the exponential is the whole structure, just like I said before for the product. It's the whole structure. Okay, so let's check that this thing works. I take the transpose of f, and I give this function here, which
one argument, returning values in the set of all functions. And now I put it right here. So this is the function which is f bar crossed with the identity on A. It takes an argument here to an argument here and an argument x here to this. And now I compose with evaluation. What happens if I say evaluate after f bar cross 1A applied to some argument? So let's take an argument down here. That's going to be a pair xa. What does it give us? Well, first of all, I evaluate, and now I apply this thing. So that's f bar of x, and then here I just get a, because that's the identity function on A, right? And now the evaluation of f bar x to A is f bar x of A, which I already said is f of x. That's the definition of f of xa. So that's exactly f. Yep. So the idea is that this universal property captures this idea of currying and evaluation, yeah? But it does it wholly in terms of products and composition and universality. So let's look at some other examples. Yep. Okay. So in the category of posets, it's easy to see, just the way that I did for products, that we can also make exponentials by equipping the function, by restricting the function space and then equipping it with the right kind of structure. So let's just do that quickly. So in posets, let's take the exponential of two posets P and Q. There I'll take all the functions from P into Q, but not all of them simpliciter, rather all the ones that are monotone. And then I'll order them f less than or equal to g pointwise. Okay. For all x and p, f of x is less than or equal to g of x. So that gives me the ordering on the set of all functions. And then the rest of the operations I can simply restrict. I can say Evaluation is just set theoretic evaluation. And if I have X cross P in any monotone map G, then I take the transpose to be the set theoretic transpose. G bar. I don't know why I'm writing G. Oh, I guess I've used the F there. Then I just take the set theoretic transpose, and now what you have to check is the following. You have to check that the set theoretic evaluation map is actually monotone. Because I've defined the ordering here, I'm given the ordering there, I've defined the ordering on the product already in terms of the orders here, and that, I've said, is the set theoretic evaluation, so that's a well-formed problem now to show that this really is monotone. And then, given a monotone map like this, I'm taking the set theoretic transpose, it's called here, the associated thing here, and you have to check that that one's monotone with respect to the ordering that I defined there. And once that happens, then you know that this commutes because these were set theoretic operations. And then you're done. Right? So that's a sketch of the proof that POSETS has exponentials. Yeah.
Why the name that order elements of Q to the P are written?
You don't need that, but we're trying to find a POSET which will have this property. And now I happen to know that this does it. You could try something else. This is exactly like the question, why did you order the product in the way that you did? This is the ordering that satisfies this universal property. And once you check that it works, then you know that that's what it must be. It's determined uniquely because it wants this by that specification. You could try other things, right? And then you'll struggle and you'll find it doesn't work. And eventually you'll either give up or you get on this, and then you'll say, oh, that must be it then. Does it make sense?
What is word that defines that the element of Q to the P are monotone?
In this proof, why you need in the proof, you go through the details of the proofs. It's a good exercise today.
But is the idea of why we put monotone here, is the idea that the exponential object must look like a function in this case?
Yeah, sure. Yeah, this is a special case of something much more general, namely for two categories, D to the C. We can make a functor category, yeah, and that will be an exponential cat. And we'll do that next time, but not yet, because here I need to say what the maps are between functors. The objects will be functors. The maps will be natural transformations. And that's the subject of this. And then we'll show that that is an exponential cat. Here, this is a special case of that. These are exactly natural transformations between these functors. Okay, so that's exponential.
How about, oh, there's a homework exercise that I want to mention. I don't know if you can do it or not, but you might be able to do it, so it's worth a try. What about groups? Could you make an exponential of two groups, h to the g? Maybe you would try to say it's all the homomorphisms from g into h. Homomorphism. And then you'd have to say what the evaluation is and so on. So you could think about that and try to make that work. And the homework exercise is to show that this doesn't work. And there's a trick. Doesn't work. And the observation that you need to see that it doesn't work is that in any... Oh, wait, I need a little bit more information here. Let me hold that thought right there and go over here and finish up a definition, and then I'll come back to that. I wanted to find the notion of a Cartesian closed category, and I need one more little bit of data, and then we'll have it. And then I can go back and show you what I have in mind there for groups. So a category is Cartesian closed. Cartesian closed. if it has the following, well, it has products for any pair of objects. It has exponentials for any pair of objects. Of course, what I mean here is together with the rest of the structure. And then it has what's called a terminal object, which is a particularly trivial universal mapping property. Terminal object. So what's a terminal object? A terminal object, by definition, is this. Say 1. So here's the definition. 1 is terminal if for any object A there exists a unique map. Here, I'll use my convention there. A unique map down to 1. So for all A, there's a unique map from A into 1. So that's a kind of degenerate universal mapping property, isn't it? It has the existence and uniqueness built in there. And of course, any two terminal objects are going to be isomorphic, just because it's a universal mapping property. And just to give you a sense of what's going on in sets, any singleton set, any one element set is terminal. Similarly, in posets, same thing. In a poset, what's a terminal object? Well, it's an object such that any other object is below it, so it's a top element. Top element in the poset. Initial object, by the way, is the dual here, so that's the bottom element. That's the empty set in the category of sets is an initial object. Okay, so Cartesian closed category, I want to have not only binary products, but I want to have a terminal object as well. And then I want exponentials. And now let me observe that the universal mapping property of the exponent implies the following two-way rule. Anytime I have where is it? It's over there. X cross A, a map from X cross A into B, then there's a corresponding map from X into B to the A, right? That's this transpose business. Given F, there's a transpose like that. However, anytime I have a map like this, I can cross it with 1A and compose with evaluation and get a map like that. Given any map like that, some G here, I cross it with 1A, compose with evaluation, and get a map over here. Yeah? The universal mapping property says exactly that this correspondence, this two-way rule, is an isomorphism. Everything like this comes uniquely from a thing like this by that recipe crossed with A and composed with evaluation. Make sense? So the assignment that goes from here to here is take, the assignment that goes up the other way. The assignment that goes from here to here is take F bar, cross it with 1A, and compose it with evaluation. Take evaluation, compose with F bar, cross with 1A. Right? The universal mapping property says, given any one of these, there's a unique one of those, such that when you apply this operation, you get this thing back out. That's exactly what it says. So it says exactly that this is a bijection. We have this kind of two-way rule. It's just like the rules that we had for the product over there. And maybe this is a good time to emphasize, I haven't forgotten this uncached check over there. I need to finish that sentence, but maybe this is a good time to emphasize the following. So, look. These universal mapping properties are like rules of inference, schematic rules of inference. right? For the product, it looked like this. It said, given any x into A and x into B, you get a map from X into A cross B, right? So if this is the F and this is the G, then this is the paired up F paired G. And given anything here, you compose with the two projections and you get these two things. So that's a kind of two-way rule of inference, right? For the coproduct, so that was for the product. For the coproduct, it looks like this. It says, given any A into X and any B into X, you get A plus B into X. That's the co-pairing of those two maps. And given this one, you precompose with the two injections, and that gives you these two. What is the one for the exponential? Exponential. It says, well, it's that. It's that right there. Given any X cross A into B, you get X into B to the A and back, okay? And the recipe for getting back and forth is just this one that I've written down. So another way of stating universal mapping properties is in terms of bijections between maps of different shapes. So it looks like, it's starting to look like rules of inference for a deductive calculus. And in fact, that's what, if I have time, I hope to make that more precise. Okay, so now, what if we look at the case where X is 1? What do we get? What are maps out of a terminal object? They're like constant elements or points of a thing. So consider the case of X equals 1. Then we have 1 cross A into B corresponds to 1 into B to the A. Now, it's an easy exercise to show that when you have products in a terminal object, that this thing is isomorphic to A itself. So this is saying that maps from A to B correspond to points of the exponential, constant elements of the exponential. Yeah. So now, so that's the observation that I want to use to finish the sentence over there. In any CCC, points of the exponential here correspond to maps from G into H. But now suppose that this thing is a group. Okay? 1 is the terminal group. It's the one element group. It only has a unit, a group unit. And every homomorphism takes the unit to the unit. So there's only one homomorphism like this. If this thing is a group, there's only one map like this. And therefore, there can only be one map like that. So in general, if you have two groups, there are going to be lots of maps here. And so that's a sketch of why the category of groups cannot be Cartesian closed. Okay? Because if it were Cartesian closed, you would only have one map here, and therefore you would only have one map here. However, there's a more general notion of a groupoid. Remember, a group was a category in which every arrow is an isomorphism, and you only have one object. Well, let's throw out that only one object business, and we look at a category in which every arrow is an isomorphism, full stop. That's the notion of a groupoid. And now you can show that there's no problem with assuming if this is a groupoid and this is a groupoid, then this thing is a groupoid, and in fact, you do get then a Cartesian closed category. So that's a good exercise, but it's a more challenging exercise. It requires that you go through various steps and think about it. But it's good to think about it. And next time when we do functor categories, the special case of groupoids will be exactly the case where these things are each groupoids, and then you make the functor category, and you get the exponential in the category of groupoids. All right, so I have a few minutes left, and really the whole point of this lecture was to connect up now with the lambda calculus. So let's do that without further ado in order to show that we have examples of all of these structures in the lambda calculus too. So the first thing I want to do is look at an example of, okay, so we're done with that, right? I can use this board. So let's look at exponentials in a POSET. What is an exponential? Exponential in a POSET. P. So an exponential in a POSET would be a thing like this. So let's keep writing x, y, z for the elements of P. I'm going to use A, B, C too. So what would an exponential be? It would be an object b to the a, and it would have to have the following property for any x. If x is less than or equal to b to the a, then x cross a is less than or equal to b. But the product we know is a meet. So does that look familiar? Let's see. We need to have a gadget here which has the property that it's greater than any x, which when met with a is less than or equal to b. Well, that's usually written as a kind of implication in a POSET. Let's write it like that, a arrows b. So, so the idea is we have a arrows b is a new element of the POSET, and it satisfies this condition. So, for example, in propositional calculus, say intuitionistic or classical, this really is the A arrows B is the implication. So let's just check that that's the case for an implication in the propositional calculus. We need some rules. So let's take a propositional calculus with some variables and formulas that we build up in the usual way from conjunctions and implications. And we can put a constant true in there too if we want to. And then we'll have the rules. We can give them in any form we like. But let's just, to be specific, let's take a natural deduction setup. So if we have A and we have B and we have B, then we can infer this. And if we have this, then we can infer this, respectively, this. And if we have A and we have A arrows B, then we can infer B. And if we have a proof of B coming from a hypothesis A, then we can cancel the hypothesis, the assumption there, let's label it U, and we can get A arrows B without any assumptions. So that's a kind of abbreviated or typical natural deduction setup for that fragment of propositional logic. Since we have true in there, we might as well allow ourselves to infer true from anything or from nothing at all. And now we need to check. So first of all, let's see that we really have a category, because I want to say that this thing is a Cartesian closed category, but I haven't said what the category structure is. So let's make a category, and the arrows will be implications. That is, if there exists a proof, right, right, so this is, there exists a proof, so that's what last time what I called P, B, but now I'm saying if there exists a P such that A proves B, so those will be my arrows in the category. Good? It's obvious, I think, that A has an identity arrow and that we have a composition. You can just put the proofs together to get implies A, C, and that this is a pre-ordered category. That is, there's at most one arrow between any two things, just by the way I've defined the ordering here. So that's my category. The objects are formulas in propositional calculus. The arrows are the deducibility relation. It's a pre-ordered category. And now the rules for the conjunction obviously make conjunction a product. this is a product. The top is a terminal object, and we just want to check that this is an exponential. So what do we have to check? We have to check that if x is less than a, or if x proves AB, then A proves B, and conversely. So let's check. Let's suppose that, this is an easy exercise, we'll just do one direction. Suppose that x proves A, B, and now we want to get this. So take x, A, and we want to get B out of it, right? So first of all, we'll get the x, and then we use our assumption to get A arrows B. And then we use this assumption again, A, and we get the A. And now we apply A and A arrows B to get B. So that's our rule of elimination there. And that's the direction from top to bottom, right? And similarly, the other case will follow equivalently. And now you might wonder, well, what's the evaluation here, right? Because I have the two-way rule, but I haven't shown you what the evaluation is for the exponential. So the evaluation, the exponential, it should satisfy A arrows B and A proves B. So we have to check that there is a proof like that. Well, it's easy, right? You take the two projections and then you apply the rule for functions to get the B out. So that shows us that this propositional calculus is Cartesian closed, and that the implication operation in propositional calculus really is an example of an exponential in a category, just like the function set in the category of sets is an exponential. It satisfies exactly the same rules. What if we take, instead of the provability relation, if we take the category of proofs that we talked about last time? So let's do that. So instead of the propositional calculus, we'll now annotate all of these proofs with proof terms in order to get the lambda calculus out of this. So in light of the short time, I'm not going to rewrite it. I'll just say, take here some proof terms, right? Say alpha, beta, and then we take a pair, alpha, beta. And here is a projection. So if this is a gamma, then we take pi 1, say, or first of gamma has this type, second of gamma has this type, right? So if this is alpha and this is beta, and this is beta applied to alpha, and this is a lambda abstraction here. So if this is gamma and this is a variable u, then this is lambda u gamma. Yeah? So now we're doing something richer than just this category of provability. We're doing actually the category of types that I think I talked about last time, didn't I? So now instead of this, I say this, and now I have real different proofs from A to B. There can be lots of different arrows from A to B. So this is no longer the case. I say P is an arrow from A to B if P is a proof, if P is an actual proof of A to B. So I take A, and I take P here, and B. And there can be different ones, right? Q, and so on, and so on. But it still is a category. It has identity arrows. It has composition of arrows. And now I would like to check that this category of proofs, it's also called the category of types. So category of types. Thinking of these things now as types in the lambda calculus rather than as proofs in the propositional calculus by the Curry-Howard isomorphism, right? Doesn't matter whether I regard them as proofs in the propositional calculus or as types in the simply typed lambda calculus in terms of those types. So it's category of types in the lambda calculus, simply typed lambda calculus. And now I claim that this is a Cartesian closed category. So let's just check that that really is the case. Well, think it's almost immediate, right, that these are going to give projection operations coming from this is going to be the product, this is going to be the projection operation, right? This is going to be the pairing associated with the product. This is going to be the transpose of a function that we needed before. And then the evaluation, I think you can figure out for yourself, comes from this, right? If I take the object that's the product of these two things, take the two projections, and then I apply one to the other, that's going to be the evaluation. Yeah? So I think I won't go through the details except to note that to make this a Cartesian closed category, it turns out that we need to identify certain proofs. We don't need to do it to make it a category. It just is a category. We checked that last time. But to make it really be a Cartesian closed category, we need to identify some proofs. And in fact, it's easy to say which proofs need to be identified. It might have been that the congruence relation or the equivalence relation on proofs was something that's really hard to specify, right, in order to make it Cartesian closed. But it turns out it's very simple to specify. It has some familiar axioms. Namely, if we take two proofs, alpha and beta, and we pair them up, and then we take the first projection of that, we need to identify that with the proof alpha. If we think about what's happening, right, in natural deduction, we're saying, well, take a proof of A and a proof of B. Let's switch to uppercase here just for fun, right? And then take the pair alpha, beta. That's a proof of A and B. And now take the first projection. Well, now we've got a kind of a detour here, which started out from a proof of A, and it ends up with a proof of A. And now what I have to do is identify a proof that goes straight to A and a proof that goes all the way to A through such a detour. Yep. Yep.
Is it possible to weaken the definition of CCC?
Yeah, sure.
Not have to do with the
Yeah, it has a certain structure, but those things are not universal. Right? It has a kind of a weak CCC structure. So similarly, we have to do it with a second projection, and then we have to add the rules of lambda conversion, right? We have to say that if I take lambda x of some beta, and then I apply that to some alpha, say that that's beta with alpha for x, and similarly, if I take lambda x of f applied to x, that that's f as long as there's no free x in f. Well, these are just the usual rules of beta-eta conversion, right? So that's what's sometimes called beta-eta equivalence. So if you add the rules for beta-eta equivalence plus the congruence laws that say substitute equals for equals everywhere, and you look at the congruence that's generated then on the set of all the lambda terms, it gives you a new category, and now that category is actually Cartesian closed. So it's easy to kind of check it. It's routine. It's in the notes. But you should think through it yourself or read it for yourself. And it shows you that this category of types in the lambda calculus really is a Cartesian closed category. Now, I'm out of time, but I would like to mention one consequence of this fact, which I think is worth noting. We've actually done the proof. It's just a question of formulating the fact that we have just established in a different way in terms of deductive completeness of the calculus of beta-eta equivalence. So we could say, let's define a theory in the lambda calculus, theory T in the lambda calculus, to be the following. We have some basic types, and some basic terms, which we throw in. They don't have to be of basic type. They can be of any old type. So let's say A of type X. And some equations between terms of the same type. And we can have a whole set of types, a set of terms, and a set of equations. And then we generate, using the beta-eta reduction, that is, using these equations plus those equations and substituting equals for equals, we can define this notion then of T proves, for some terms here, let's say S and T, well, some other terms, A equals B of some type X. So that's a relation that we're interested in. It's the algebraic theory determined by those basic types, terms, and equations, right? So for example, you could formulate the theory of groups in this way as a lambda theory. You could formulate any algebraic theory in this way as a lambda theory. But you can also formulate some higher order theories in this way because we have function types as well. And so we can have terms of function type. A nice example is Dana Scott's theory of a reflexive domain. This is a domain D such that when you make D to the D, you can have a embedding retraction pair or even an isomorphism between these two things. So put in a section and put in a retraction and then put in an equation that says that R after S is the identity on D to the D. You could do the other one too. S after R is the identity on D. So there's an example of a theory in the lambda calculus. It has one basic type, two basic terms, and two equations. So there are lots of such examples of a theory in the lambda calculus. And then define a model. Define a model of such a theory T in a Cartesian closed category C. Well, that's an assignment of basic types to objects in C, and basic terms, say A, should then be, if it's a closed term, it should be a map like this, or the corresponding thing in C. So in C, such that, and now what I have to do is extend using the Cartesian, so this is the assignment of the basic data, yeah? And now I extend to all terms. So now extend, given this basic data, extend the interpretation for any term, T1 into, say, some type A for any T of type A, and in particular for any term F of type A arrows B, then I get an interpretation F as an arrow in my Cartesian closed category. And so now the definition of a model is I assign the basic data like this in the Cartesian closed category, I extend it to all terms like this, and then when I interpret my things occurring in the basic equations, S and T, S actually comes out to be equal to T in the as terms of type X. So if you specialize this to familiar cases like the theory of groups, and you interpret it in the Cartesian closed category of sets, a model will just be a group. Okay? So it captures the usual notion of a model of an algebraic theory. If I do this for that theory, a model of that theory will be what's called a reflexive object in the Cartesian closed category. It'll be an object D such that the exponential of D with itself will admit a retract from D. Yeah? A section retraction pair from D. So it captures exactly kind of the intuitive notion of an interpretation of the lambda calculus into a Cartesian closed category. And now the theorem is the completeness theorem. The theorem says so this is something like Cartesian closed category completeness for lambda calculus. for any theory T in the lambda calculus. One, the following are equivalent, or let me put it this way. For any terms, closed terms say, closed terms. We can always close them up by changing the type. For any closed terms, A and B of any type X, if T proves A equals B from the axioms for the theory, the basic equations for the theory, then, and only then, is it the case that the interpretation of A equals the interpretation of B in any model, or every model, T model, of course, in any Cartesian closed category. So if T proves it, then it's true in every model, and moreover, if it's true in every model, T must prove it. So it's just like the completeness theorem for first-order logic with respect to set-valued semantics that we've already talked about, but now we're talking about provability in the lambda calculus, and the semantics are in Cartesian closed categories. And then another notion of provability in the lambda calculus is the existence of a closed term of a type. That corresponds to the lambda calculus as the proof theory of propositional logic, because the existence of a closed term of a type means there's a proof of the corresponding proposition in, say, a natural deduction calculus for the propositional calculus. So there exists a closed term, say T, for some type X, just in case in every T model in a CCC, the type interpreting X has a map from the terminal object. So there exists a map from the terminal object. So it's a very strong sense of completeness. It's completeness in this deductive sense, and it's completeness of beta-eta equivalence with respect to CCC models. So what this tells us really is that you can, the lambda calculus, in a certain sense, the lambda calculus, at least with the simply typed with products and function types, is really equivalent in a sense that, if I had more time, I could make precise as an equivalence of categories to the notion of Cartesian closed category. There's a way to turn any lambda calculus into a Cartesian closed category, and there's actually a way of going back, and we could define morphisms here and get an equivalence of categories. It's a very tight, precise correspondence, which can in fact be cashed out like this in terms of a completeness theorem. And it's quite nice to look at the, if I can just say one more thing, this was the proof theory of propositional logic. We can do a similar thing here with the propositional logic itself, intuitionistic propositional calculus, say with conjunction, implication, even with disjunction, is going to be in exactly the same way equivalent to the notion of a poset CCC. Well, let's do it without the disjunction first. A poset CCC is just a Cartesian closed poset, right? It's like this first example that we had of the intuitionistic propositional calculus as a poset. But we can also add the other operations here, for example, the disjunction, and then we get the notion of a Heyting algebra, respectively Boolean algebra. Let me spell it out. So I don't have time to do that, but exactly the same correspondence holds here, where this is the kind of poset collapsed case of this, which is the proof theory of the thing. Okay, so that's enough for now. Next time I will talk about naturality, natural transformations, and there's a special case of this completeness theorem that's of some interest, and that is looking for specific Cartesian closed categories which suffice to test for completeness. These are general abstract Cartesian closed categories. It's very interesting to know that this completeness theorem holds as well when you specialize to Cartesian closed categories of a very special form, namely functor categories, or even functor categories where the exponential category in the exponent is a poset, P, and these are, I think, reasonably called Kripke models. So there's a Kripke completeness theorem for the simply typed lambda calculus, which follows from this result by a kind of specialization result about special Cartesian closed categories of this form. Okay, thanks a lot.